Today I'm gonna talk about the graph topology identification. So somehow related to the last part of Bish's presentation. But now we focus on the graph doesn't change. We want to estimate the graph in static case. So it's can be much easier, but because we have prior information of the model, so we will dive into this deep later. So firstly, why we want to do graph topology identification? Because usually what we know is just data from the entity, from nodes. But what we care about is not this data. We care about the underlying relationship. So we somehow want to know the relationship between this data, behind this data, but from the data we have observed. So like in the brain network, so we want to know how your brain functions. So what we can only get is a signal from every part of your brain. And also for the social network, we want to know the relationship between the users. But what we get is some data of every user. So this is a general process of how we think about the graph topology identification. So we have a graph S, and there is some distribution based on S, that is Fs. And from Fs, we get a lot of samples, and this is our observation data. And after we get a lot of data, we want to infer what is S. So usually we have some assumption on the F. So for example, it can be Gaussian distribution. So if it's Gaussian distribution, we just need to know the mean and the covariance. So the mean and the covariance are both determined by S. There are also some kind of assumption on F. For example, smoothness, they let the signal to be smooth on the graph, and for graphical zone, they want to estimate the precession based on the sample covariance. And for spectral templates, they think the somehow the eigenvector of S is the same to the eigenvector of your sample covariance. And here, what we're going to talk about is a structure equation model, or SAM. So this is how SAM looks like. Is X is equal to Sx plus E. So S is a graph we want to estimate, and X is what we observe. And we can solve X from E. And E is something we don't know, but this is something that creates the randomness. So here we model E to be a Gaussian, actually white Gaussian here. And we assume S to be some kind of easy thing we can handle. So S is an undirected graph, and it doesn't have safe loop. So in this case, we can know the distribution of X. That is also a zero mean, and the covariance is I minus S inverse power 2. So you can think we have T samples. Then we can collect all the data together. We get a big data matrix X. So very easy idea, or easy to think about the idea, is to do signal match. This is because the E is zero mean. So we naturally want to think about what if E is zero? Of course, as X is equal to Sx. So then we just need to find a regression problem, and based on the constraint is easy because it's convex. So this one we can find the closed form solution, but actually this is not the maximum likelihood estimator. This you can think about it, because you have let's say we have a Gaussian. We know something is Gaussian. We want to estimate it, and we get a sample covariance here. And if we want to match these two distribution, you would have a log delta term. yeah, I don't know if I should introduce this. Okay, but actually, if you add a log dirt term here, so this one gonna be the max likelihood estimator, but the log dirt is something very non-convex and hard to handle. So this can be regarded as a simplified form of the max likelihood estimator. And this approach is only work for DAG, because for DAG the log dirt term it vanish, it's a constant. And also if we have some extraneous variable, we can also have a good estimation result. That means we have additional information on what is a mean. It looks like that. So and this some experiment to verify our idea. We run a simple regression problem, and actually we can prove. Yeah, we can have a very strong proof. Even the t goes to infinity, we still for any graph S, we cannot get the true. Sorry, I mean the estimation result doesn't convert to the true graph S. So that's a problem. We want to improve it. So let's back up to the idea, just a simple Gaussian stuff. So how can we determine a Gaussian distribution? We just need to know the mean and the covariance. That's enough. So our idea is pretty simple because the mean is 0. The only thing we can track is the covariance. And from the sample, we can also get the sample covariance. So we want to make the sample covariance and the expected covariance if we know the S hat. So we want to make them to be as close as possible. And of course, we have the constraint on S. So the way we solve it is, but this one is hard to solve. The way we solve it is we somehow switch the role of constraint and the objective, because the constraint you say is very simple, it's easy to handle, but the objective is something hard to minimize. So the way we minimize is we want the object to be 0, but we need make the constraint as close as possible. So we can the trick we use is we take the eigenvalue decomposition on both sides of sample covariance and the expected covariance. So here you can see, to make these two stuff to be equal, we just need to make the eigenvector and the eigenvalues to be the same. That's enough to make the objective to be 0. So for eigenvector, this is simple. You just make the u hat to be ux, that's enough. But for eigenvalues, because here we have a square, so this means we have a sign ambiguity here. So this is something we want to. It's not easy to make, and something we need to optimize. So and here to guarantee the diagonal constraint, we just replace the s hat with a new variable u hat and the lambda hat, and we get the constant here. Okay, so to do optimization of the diagonal, we just need to so we firstly switch the role of the constant and the objective, and we get a new optimization problem. And you can see here it's just a sign ambiguity. So somehow, if we introduce a binary vector q, and this is to indicate the psi of the eigenvalue, and the constraint is naturally satisfied, because no matter it's -1 or 1, the square is just 1. So in this way, we only have the objective we need to handle. And here, because we introduce q, we can reduce this to the form just as a binary quadratic programming form. So and this problem we have many methods to solve. No matter you can do some search-based method or we can relax it. Like that is we don't estimate the Q, we estimate the capital Q, and the capital Q is Q transpose, and we relax of course the rank Q is equal to 1, and we relax the rank constraint and we can solve for the Q. And here is the result we get, and we can also compare to other methods. You can say actually our result is as the sample goes to infinity, we can have a very low error. This means we can find the true graph. And for the very simple, a very simple signal match method, which is two line here, you can say actually it cannot go to the true graph. And also there's another method called spectral template. It can go to the true graph, but in some hard case, it works not that good. Okay, so and we also want to extend our method to like a more general model. So first thing, because we just do sample covariance, for any model, once you know this, you can calculate the expected covariance. You can match the expected covariance and your sample covariance. So the first model we think about is a polynomial model. So this means x is equal to hs times e, and hs is a polynomial on S. And here again we can calculate the expected covariance if we know S. And you can regard this as a special case of the SAM, because in SAM, hs is equal to I minus S inverse. So here we wish to match the CX, the sample covariance and the expected covariance. And again, we can also do eigenvalue decomposition on S and the eigenvalue decomposition for sample covariance. And here we also get for the eigenvector, we just need to make them to be equal. For eigenvalue, we get a polynomial equation. In SAM, this polynomial equation gives us a psi ambiguity because it's just a second order polynomial. But here we have something more general. This one depends on the order of your each. So this one can have more than two solutions. So the way we solve it, we also have two methods to solve it. One is very similar to the rank relaxation method, but here we can also do relaxation for this problem. Another is you do some kind of branch and bound method. You can still this can find the global minima. Okay, and very similar we get the even the very similar form. So this is if a lambda hat can only take two value, it's similar to the binary quadratic programming, but now lambda hat can take several candidates. So this is a discrete optimization problem. So another extension we have done is we now do like if we now the E is not white or standard, we want it to be colored, but remember we know what is a distribution of E. So here again we can calculate the expected covariance that is based on the S. So again, if we want to match the sample covariance and the expected covariance, this is we want to match each sigma E A transpose to be CX. But this one is hard to handle. Remember in the SAM we have a form like something square is equal to something we know. So this form is something we want. So we multiply both sides by sigma E. So in this with the left side is just h hat sigma e square, and on the right side is something we know. So this is something we prefer, and again, like the previous step, we can do eigenvalue decomposition on both sides. So for the sample covariance, we do eigenvalue decomposition, and for the expected covariance, we also do eigenvalue decomposition. And here you can see we still have a sign ambiguity here. The only difference is now the U is not a unitary matrix, because now the H sigma E is not a symmetric matrix. So you actually here what you get is a general matrix. It doesn't need to be unitary. And again, we still want to switch the objective and constraint, and we get a very similar form. Some matrix have a binary variable -1, and we want to minimize this value. And this one can be solved in a very similar form. And here, we compare some results. So here we have a sum for the sparse graph, and also because here we actually don't use any sparse here. This method can also be used for fully connected graph. It doesn't need to be sparse. So and also here we do some experiment on the polynomial, and here the polynomial is order 3, so it's not a very low order. So you can see we actually get a very good result, and the error goes to very small as the time goes to infinity. Yeah, so this is what we have done in my master thesis. So we should introduce a covariance matching method, so that can this actually the solution is close to the max-select-pole estimation. And because now we get a very good starting point, actually we can still use this as a starting point for the max-select-pole estimator. And there's no scale ambiguity in this method, because for the spectral candidate, actually you know the graph, but there is a scale ambiguity. So any scalar times graph is actually something you can get. And also, yeah, this is some future work we can extend it to directly, and also introduce some sparsity here, and even some dynamic or changing graph. Okay, thanks.